Download this code from codegive.com, link in the description below. OK, let's dive into a comprehensive tutorial on controlling an ESP32 from anywhere in the world. We'll build a system that allows you to remotely toggle an LED connected to your ESP32 using a web interface. This tutorial will cover setting up the ESP32 environment, Arduino IDE, writing the ESP32 firmware, web server, securing communication, HTTPS, setting up port forwarding, or a cloud service, creating a web interface, HTML/JavaScript, putting it all together. Prerequisites ESP32 development board, LED and appropriate resistor, example 220 ohms, Arduino IDE installed, a stable Wi-Fi network, a computer with internet access, basic understanding of HTML, CSS, and JavaScript, optional but helpful. Step 1, setting up the ESP32 environment, Arduino IDE. 1. Install the Arduino IDE *. If you haven't already, download and install the latest version of the Arduino IDE from the official Arduino website, https://www.arduino.cc/n/software, https://www.arduino.cc/n/software. 2. Install the ESP32 board support package *. Open the Arduino IDE. Go to File-Preferences. In the Additional Boards Manager URLs field, add the following URL. Click OK. Go to Tools Boards Manager. Search for ESP32 and install the ESP32 by Espressif Systems package. 3. Select your ESP32 board *. Go to Tools Dashboard and select your specific ESP32 board model, example ESP32 Dev Module. Set the appropriate Tools dashboard for your ESP32. It should show up as a COM port, Windows, or /dev/tty, Linux/Mac OS. Step 2, writing the ESP32 firmware, web server. This is the core of the project. We'll create an ESP32 sketch that acts as a web server, responding to HTTP requests to control the LED. We'll also implement HTTPS to secure the communication. Important notes about the code *. Your _Wi-Fi _SSID and your _Wi-Fi _password *. Replace these with your actual Wi-Fi network credentials. LED pin *. Change this to the GPIO pin to which your LED is connected. The LED should be connected in series with a resistor to limit the current. HTTPS and fingerprint *. Crucially, you must generate a self-signed certificate and obtain its SHA-256 fingerprint. I'll discuss certificate generation below. Replace the placeholder fingerprint string with your actual fingerprint. Without a valid fingerprint, the HTTPS connection will fail. Step 3, generating a self-signed certificate and getting the fingerprint, essential for HTTPS. Since we're aiming for secure communication, we'll use HTTPS. For testing purposes, we can generate a self-signed certificate. However, be aware that self-signed certificates are not trusted by browsers by default and will produce a warning for production environments. You should use a certificate from a trusted certificate authority, CA. Here's how to generate a self-signed certificate using OpenSSL. 1. Install OpenSSL *. If you don't have it already, install OpenSSL. It's available for Windows, Mac OS, and Linux. To generate the certificate *, open a terminal or command prompt and run the following command. This command will *generate a new RSA key, key.pem. *create a self-signed certificate, cert.pem, that's valid for 365 days. You will be prompted to enter information such as country, state, city, organization name, etc. These are not critical for this test setup, but fill them in if you wish. 3. Generate the fingerprint *. This will output the SHA-256 fingerprint, e.g. SHA-256 fingerprint equals
30:47:20:37D034A52:21:30:78:79:89:76.
Copy the hex values, without the SHA-256 fingerprint equals part, and paste it into the fingerprint variable in the Arduino code, removing the colons. Important security note: self-signed certificates are acceptable only for testing. For a real-world deployment, you absolutely must use a certificate from a trusted certificate authority, CA. Let's Encrypt offers free certificates. Step 4, SPIFs setup. SPIFs is a file system that allows you to store files on the esp32's flash memory. We'll use it to store our HTML, CSS, and JavaScript files for the web interface. 1. Install the esp32 Sketch Data Upload Tool ***. In the Arduino IDE, go to Sketch-Include Library-Manage Libraries. Search for esp32 Sketch Data Upload and install it. 2. Create a data directory ***. In the same directory as your Arduino sketch.ino file, create a folder named data. 3. Create index.html ** inside the data folder, create an index.html file with the following content, or something similar. 4. Upload the data folder to SPIFs ***. In the Arduino IDE, go to Tools-ESP32 Sketch Data Upload. This will upload the contents of the data folder to the ESP32 SPIFs partition. This step initializes the flash with the HTML page. Step 5, Setting up port forwarding, or a cloud service. To access your ESP32 from anywhere on the internet, you need to make it accessible. There are two main approaches. Port forwarding, less secure, but simple for testing. This involves configuring your home router to forward external traffic on a specific port to the ESP32's local IP address and port. Cloud service, more secure, scalable, and reliable. This involves using a service like ThingSpeak, Adafruit.io, Blynk, or similar platforms to act as an intermediary between your ESP32 and the outside world. Option 1. Port forwarding, use with extreme caution, only for testing. 1. Find your ESP32's local IP address *. Look at the serial monitor output from your ESP32. The code prints the IP address. 2. Access your router's configuration page *. Open a web browser and enter your router's IP address, usually something like 192.168.1.1 or 192.168.0.1. You'll need your router's username and password. 3. Find the port forwarding settings *. The location of these settings varies depending on your router's manufacturer. Look for options like port forwarding, NAT forwarding, or virtual servers. 4. Create a port forwarding rule ***. External port *. Choose an external port, example 443 for HTTPS, but you can use a different one if desired. If you use a port other than 443, you'll need to specify the port in the URL when you access the ESP32. Do not use port 80 for HTTP, as it's insecure. Internal port *443, or whatever port your ESP32 web server is listening on. Internal IP address * the ESP32's local IP address. Protocol * TCP. 5. Find your public IP address *. Go to a website like whatismyip.com to find your public IP address. Danger. Warning. Port forwarding exposes your network to potential security risks. Only forward the necessary ports and use strong passwords for your router. Using a cloud service is almost always a better option. Option 2, using a cloud service, recommended. This is the recommended approach for a more secure and robust solution. Here's a general outline using a service like Adafruit.io. The steps will be similar for other platforms. 1. Create an account *. Sign up for an account on Adafruit.io, https://io.adafruit.com/ https://io.adafruit.com. 2. Create a feed *. Create a feed to represent the LED state, example named LED state. 3. Install the Adafruit.io Arduino library *. In the Arduino IDE, go to sketch-include library-manage libraries, and search for Adafruit.io Arduino and install it. Also install the Adafruit MQTT library. 4. Modify your ESP32 code *. Replace the web server code with code that connects to Adafruit.io, subscribes to the LED state feed, and updates the LED based on the received value. You'll need to use the Adafruit.io Arduino library functions to connect to the MQTT broker and publish/subscribe to feeds. You will need to include your Adafruit.io credentials in the ESP32 code. Replace placeholders * change your _Adafruit_io username, your _Adafruit_io key, your _Wi-Fi SSID, and your _Wi-Fi password with your actual credentials. Upload the updated code to your ESP32. 5. Control from Adafruit.io dashboard * create a dashboard in Adafruit.io. * add a toggle switch or button linked to the LED state feed. * when you toggle the switch on the dashboard, Adafruit.io will send an on or off message to your ESP32, which will then control the LED. Step 6, creating a web interface, for the cloud service option. If you're using a cloud service, you can often use their built-in dashboard features. However, if you want more control, you can create your own web interface. 1. Host the web interface * you'll need to host your web interface somewhere, example a web server, a cloud storage service like AWS S3, Netlify, or Firebase hosting. 2. Use JavaScript to communicate with the cloud service * use JavaScript to make API calls to the cloud service, example Adafruit.io's REST API or MQTT API, to update the LED state feed. Here's a basic example using JavaScript and the Adafruit.io REST API. Remember to replace your _Adafruit_io username and your _Adafruit_io key with your actual Adafruit.io credentials. Step 7, putting it all together. 1. Upload the ESP32 code *. Upload the appropriate ESP32 code, either the web server code with port forwarding or the cloud service code, to your ESP32. 2. Configure port forwarding, if applicable set up port forwarding on your router if you're using the web server approach. 3. Access the web interface * port forwarding * open a web browser and enter https://your _public_ip your _external_port, replace with your public IP address and the external port you forwarded. You'll likely get a warning about the self-signed certificate. Accept the risk, for testing purposes only. Cloud service open the Adafruit.io dashboard, or your custom web interface, and use the toggle switch / button to control the LED. Troubleshooting Wi-Fi connectivity double check your Wi-Fi credentials and ensure your ESP32 is within range of your Wi-Fi network. Serial monitor use the serial monitor in the Arduino IDE to debug. It will print error messages and status updates. HTTPS fingerprint ensure that the fingerprint you are using matches the certificate. Firewall make sure your firewall isn't blocking the traffic on the forwarded port. Cloud service connection check your Adafruit.io credentials and make sure you're using the correct feed name. JavaScript errors use your browser's developer tools, F12, to check for JavaScript errors in your web interface. SPIF's upload failed. Make sure that the data folder is correctly placed in the same directory of the .ino project file and the necessary upload tool is installed. This is a detailed tutorial, and it might seem daunting at first. Start with the basics, test each step thoroughly, and gradually build up the functionality. The cloud service approach is generally recommended for security and reliability. Good luck, and happy tinkering!